All right, this chapter is all about stoichiometry. So we're going to be doing all kinds of calculations in this chapter, and these are calculations that we'll use throughout the whole year. So please be sure that you understand how to do them, not just following the steps, but you understand the process. And let me know if you have some trouble, because we want to make sure you feel good about this chapter before we move into some of the harder problem-solving chapters. So first of all, we're going to start talking about the masses of these atoms. So first of all, remember the mass of an atom is only the protons and the neutrons. And that's because electrons don't weigh anything. So you would think that the mass numbers are always going to be whole numbers, because you're going to have a number of protons, a number of neutrons, you add them together and you get a whole number. You can't have like a part of a proton or a part of a neutron. But the problem is that not all atoms of the same element will have the same mass. They have to have the same protons. That's what makes them that element. But some of the atoms can have various numbers of neutrons. There can be different isotopes of the same element. So let's go through some of these statements to make sure that they make sense for you. First of all, we base these masses on carbon-12. That's the standard that they chose, and then they compare everything else to carbon-12. And the unit that we use for this is called atomic mass units, AMU. That's going to be the unit that we use for mass. You also can use grams per mole. We'll talk about that in just a few minutes. So like I said, all the other masses are compared to carbon-12, which is the most common isotope of carbon. There are other isotopes of carbon. So for example, you may have seen carbon-14 if you've talked about earth science. Sometimes they talk about radioactive dating with carbon-14, and that's how they figure out like how old really old fossils and things are. So there's other isotopes of carbon is the point. Not all of them are 12, but most of them are. And the way that we measure these are with something called a mass spectrometer. And we're going to do a whole unit on spectroscopy, which is a fancy way to say using fancy lab techniques to figure things out. So the AP exam usually has a lot of questions about spectroscopy, so I try to push that unit until close to the AP exam. Sometimes we'll do it just a few weeks before the AP exam, so it's really fresh in your mind, so you know how to answer those questions. So we're going to wait on that for just a little bit. All right, so like I said, not every element has the same mass, so what we do is we take an average. And so these numbers on the periodic table that you see under the elements, they're long decimals. And so again, the reason it's a decimal is because it's an average of all the naturally occurring isotopes of that particular element. It doesn't mean that's the mass of one particular atom. Just like if I took the average age of all of you in the class, it might be like 16.423. That doesn't mean that's how old you are. You might be 17, you might be 15, but it just is the average, so it's going to be close to it. So you can use those averages and you can round them if you need to, if you have no other information, but sometimes you'll just use the average as well. We went through that. So let's talk about how we calculate this. Let's look at this example right here. So this is a sample of neon, and there are 3 different isotopes. So we have neon 20, neon 21, and neon 22. So first of all, those numbers are telling you the mass of that particular isotope. And the reason they're different is because they have different numbers of neutrons. So again, the protons are the things that identify the element. So to be neon, it has to have 10 protons, but it doesn't have to have 10 neutrons. Most of them do, but some of them have 11 and some of them have 12. So to calculate what we call the relative abundance, it's a fancy way to say taking the average, but we're also keeping the percents in mind as well. So for example, if I wanted to take the average age of all of you, we would add up all the ages and divide by the number of students, right? That's how you do it in math. But that assumes that each student is contributing evenly to the average. And in this case, the masses are not being contributed evenly. So we're not just going to add up 20, 21, and 22 and divide by 3. That's how you would do the average in math. In this case, we have to take into account the relative abundance, which abundance means how much you have of it. So notice that we have 90.5% neon 20. Which means in any sample of neon, most of the atoms are going to have a mass of 20. Very few of the particles will have 21, and then about 9% will have 22. So we need to take those percents into consideration. And so when you're calculating this, the first thing is you want to turn your percents into decimals by bumping the decimal 2 places to the left. So we did that all 3 times for all 3 numbers. It's hard to show with my stylus. You're bumping the decimal 2 places to the left. Then you're going to multiply that decimal by the mass that it goes with. And then when you add them all up, this average takes into consideration the percentages. So notice that if we had just added up 20, 21, and 22 and divided by 3, like you would have done in math, we would have gotten 21 would be the average. And we didn't. We got 20.18. And that's because most of the neon atoms are neon 20, so the average is going to be closest to that number. So notice that 20.18 is really close to 20, but it's just a little bit higher because the other 2 masses were greater than 20. So once you get your final answer, you want to make sure that it's closest to the one that you have the most of and that it's in the direction of the other 2. So for example, if you got less than 20, that wouldn't make sense because the other isotopes are greater than 20, so it should be slightly higher than 20. All right, let's talk about the mole. So again, the mole represents a huge number of particles. It's such a huge number that it's hard to wrap your head around. If you take that decimal after the 6 and bump it to the right 23 times and add a whole bunch of zeros, that's how many particles are in 1 mole. So it allows us to talk about a lot of particles with a low number. So instead of talking about these huge numbers, we can just say that there are 2 moles or 3 moles, which is much easier than talking about all those particles. Make sure you understand these 2 sentences right here. I've seen on the AP exam sometimes they like to ask questions to make sure you understand the concept of the mole and not just how to calculate with it. So first of all, on the periodic table, those masses are not actually masses. They're called, it's a ratio of mass to moles. So it's called molar mass. So it's like when you look at oxygen, for example, it's very close to 16. So a lot of times I'll hear chemistry students say there are 16 grams of oxygen, and there's not. There's a way more oxygen atoms than 16 grams worth in the whole world. So it's not an amount. It's not a gram amount. It's a ratio. So it's how many grams you would have of oxygen if you had exactly this many particles of oxygen. It would actually be O2. So again, it's how many grams you have if you have 1 mole. So for carbon, on the periodic table, the average molar mass is 12.01. So if you have exactly 1 mole of plain old carbon, then you would have 12.01 grams, because that's the average atomic mass. But if you specify that all of the atoms in that sample are carbon 12, so none of them are carbon 14 or carbon 13 or anything else, you would have exactly 1 mole and it would be exactly 12 grams. So again, it's not just a grams, it's a grams per mole. And in fact, that's what this word molar means. It means per mole. So sometimes you're going to see something that says, gosh, that handwriting is really bad, isn't it? That says per mole. Sorry. And I just made it worse. It says per mole. I need to choose a thinner writing utensil with my stylus. So anyway, if you see molar volume, that means the liters per mole. Molar mass would be the grams per mole. So this is the mass in grams for every 1 mole of a compound. And again, it's not an amount. So you almost will never start a fence with the molar mass. What you'll do is use the molar mass to convert either from grams to moles or moles to grams. So it's a conversion factor, it's not an amount. And the last thing is if I ask you for the molar mass of something, it just means from the periodic table, and don't forget to multiply by the subscripts. So in this example with ethane, we had 2 atoms of carbon and 6 of hydrogen, so don't forget to multiply carbon's average mass by 2 and hydrogen by 6, and then you just add it all up together. And this should actually be grams per mole. Add that in there. Or you could do AMU as well. And that's about it for today. I will see you in class tomorrow.